Hello, everyone. May I have your attention, please? So today, we are glad to have Dr. John Mather, the Nobel Prize winner, with us today. And Dr. Mather, he is a senior research scientist at NASA Goddard, and he distinguished research there. The COBE project he worked with provide solid evidence and support for the Big Bang and the study of the universe. It also won Dr. Mather the Nobel Prize. And he is now leading the one of the most exciting NASA's mission, the James Webb Space Telescope, which he will be talking about today. I want to point out that Dr. Mather is not only a distinguished scientist, but he is also dedicated to education. He donated his Nobel Prize winnings to support student education, and over the past 10 years, there have been 135 students supported by his scholarship. And also, please remember that we will be holding the book signing right here after the talk. So you are welcome to stay. And let's welcome Dr. Mather.
Well, thank you for the introduction. Let me confirm that my microphone is also working. Can you hear me well? Okay, and online, I hope you can hear me well also. So I wanted to tell you the story of how we came here from wherever. We call it the Big Bang. I will explain why that's not a great name for the expanding universe. But also on the picture here to start with is the James Webb Space Telescope that I'm currently working on. It says, by the way, I'm the senior project scientist, which means I'm not the manager. I'm not an engineer. And so I can be here to talk to you about science while hundreds and probably over 1,000 people are currently still working on the Webb telescope to make it finished so we'd be able to launch it. So we'll tell you more about how it works in a bit, but basically it will be available for every human being to use. If you're an astronomer, you can send us a proposal. Right now, the call for proposals is open. Proposals are due May 1st. So astronomers everywhere will be sending us proposals. There are about 10,000 professional astronomers who will be sending us proposals. So it takes thousands of engineers and scientists and technicians to do this, and 3 space agencies, the European and Canadian space agencies, along with the NASA, of course. Now let's see if I can figure out how to work the buttons here. So, okay, just a little bit about where did I come from. This is a scientific research station in northern New Jersey where they studied dairy cows. And that was my dad's profession, a statistician working on dairy cows. And he got his master's degree here at the university, by the way, over by those little barns in the middle of campus. That was a long time ago. Anyway, this is where I grew up. I wasn't interested in the cows, but you could see the sky, unlike what you can do here. So anyway, there was a research lab in there. And they did chemistry and all kinds of interesting things that I didn't understand at the time. But anyway, I got started. So just to summarize what's been known, well, Lucretius, back in pre-BC times, actually already knew about the atomic theory. And so he was pretty aware of the main things that I might talk about today. He didn't know where the elements came from, but he was aware that a glass of water would evaporate and must do so by turning into tiny invisible particles. So there was evidence even 2,000 years ago for the atomic theory, but it took us a long time to really prove it. And not everybody knows that it was Einstein who actually got us the first real proof and measured a mass of a small particle. So anyway, if everything is made out of little tiny particles, then they stick together and grow together, and then we recognize them. Lucretius thought about linguistics also. We're giving names to things, and then after a while, things disappear. And anyway, he had a lot of it there. So what's the modern version? How did we get here? Well, we know that quantum mechanics governs everything. And if you really want to know how something works, you should, in principle, be able to say, here are Schrodinger's equations, or the more relativistic version, and solve them and say, well, that means this should happen, but that's too hard. If you want to know how does concrete work, you should get some and measure it. We know the universe is expanding, and it was very hot when it was young. We know it's very unstable. So in school, you probably taught things do not spontaneously heat up. Well, in astronomy, they do, and I'll show you a bit. Anyway, the universe has been unstable from the beginning till now, and we haven't finished understanding that, but this is one way that we identify the direction of time. So Stephen Hawking wrote a little book, which didn't really convince me, but it was called A Brief History of Time. And he's tried to explain that this is all tied together. So the universe is probably infinite as far as we can tell. Practically speaking, you cannot see past an edge. So it seems to be not curved much, if at all. So that means it should be able to continue indefinitely far in every direction. When the Greeks recognized there was something about infinity, they were pretty annoyed. But it was also pretty profound. Some people even 2,000 years ago knew about that. They knew, at least in mathematical, you could always get a bigger number by adding 1 to the number that you had. So they were able to prove that there was not a largest number. So we've learned in more recent times about DNA and stored information. My dad was working on genetics, which is stored DNA. When I was 6 years old, he told me people are made up of cells. The cells have chromosomes, and they determine your fate in some way that nobody can tell. So I thought that was pretty interesting. I wanted to know more. It was also pretty obvious that we don't all get the same ones. It's clearly not fair. Well, anyway, now you know it's not fair. It never was fair. But anyway, we also see, now that we know about this, that the interesting question is, now that we can read the code, what does it mean? So the meaning is established by the cellular mechanism that read the code and turn it into signals to do something. So that is a pretty profound recognition. Here, by the way, I talk about evolution. When Darwin recognized it, people started talking about survival of the fittest. So obviously, since we're obviously the best, we must be the fittest. So this took on a very strong moral connotation in the 1800s. Now I think we can tell better that it's more survival of the lucky. What makes us lucky? Well, who knows? Our luck seems to be that we're the ones that beat the Neanderthals. But if we hadn't turned up, maybe we'd all perished, our ancestors all perished. Maybe Neanderthals would be having this conversation. You don't know, do you? Anyway, we've also recognized in engineering that this whole process that I described is controlled by feedback loops. A feedback loop is, for instance, you driving a car, you say, I want to go straight, you steer so you stay in the line. That's one kind. As it turns out, all of our cells have feedback loops in them that you can't see, but they matter. So I have been almost completely replaced. All the atoms in my body have been replaced many times, except for a few in my teeth, and probably in the chromosomes in my nerves. But the rest, all replaced. So how does this happen? It's the control laws, the feedback loops that keep me, and well, I can still remember something, not much, from childhood. So that's pretty profound, and it has many effects on the story of Earth. So I want to talk about instability a little bit. Well, mathematically, there are a few things you can calculate quite well. In 1757, a great mathematician said, I can tell you whether this column carrying a load will collapse if we put too much weight on it. And he got the calculation, and he says, well, I know how to do it. It will collapse if the elastic energy of the bent one is less than the compressed one. So he gave us a formula. 1757, he was pretty amazing. He did an awful lot with a pencil. So we began to think about instabilities in mathematics and astronomy. About 1902, it was figured out for astronomy. When does a cloud of gaseous material, left over from wherever from the Big Bang, when is it going to collapse? And it collapses if the gravitational force pulling it together is bigger than the pressure of the gas. It turns out it comes out to be equivalent to if the time that it takes for a sound wave to get across the cloud of gas is longer than the time that it takes for the gas to fall in, then it's also unstable. So this name enabled us to figure out how fast does a star form from a cloud of gas, or how fast could a planet form from a smaller amount of gas. So over a century, we've known how to do this, but it still took us an awful long time to recognize what it meant in a practical way. So I want to talk about also emergent forms of materials. This is something people have begun to think about more recently. If I take a gaseous material, like air, and I cool it down, suddenly it gets to be different. Some of it turns into a liquid. First, the rain will condense out, and water, liquid. Then cool it down some more, the oxygen and the nitrogen will condense and turn into liquid. Well, liquids are very different from gases. They have a volume, a fixed volume, and they're compressible, but much less compressible than air. Anyway, there's a whole lot of mathematics that's been devoted to this. And so the big question is, if I take an atom off that snowflake, that's a snowflake, by the way. Did you ever see any like that? It's a real one. They used to fall like that when I was a kid. And so we don't have snow much anymore, but in northern New Jersey, we had those kinds of snowflakes once in a while. And that's a teeny weeny one, but little hexagonal columns with plates on the end. What makes that happen? It just depends on where does an atom stick best as compared to being released. So that's atomic physics, and it produces the most astonishing complexity. We look at that and say, well, that's complex. The mathematics of it's really simple. If the atom wants to escape, it has to have energy. Where does it get energy? And so this is all remarkable, and it's been figured out a lot, but not nearly enough. So, oops, what did I do? I don't know. I pushed the wrong button. Okay, thanks. Shouldn't push the button. Okay. So similarly, things that are not in equilibrium can make astonishing complexity. Here's what I call a spontaneous heat engine. Here's a great Hurricane Harvey, which had huge effect on our Webb Telescope project. But anyway, the point of this one is there is an energy flow that happens between the Earth's equator and the pole because of the geometry and the sunshine. And so a flowing energy can be harnessed by a new organization. So this is a system of circulating air that takes heat from the equator and transports it to the pole better. So that's why a complex system can spontaneously appear if it can extract energy from a flow. So basically, that's increasing the entropy of the universe by moving heat from the equator to the pole. So nature has a lot of ways to do this. And so I'm putting this here just because it's an example of nature makes complex systems when you think it's complicated, but it's just another way of increasing entropy. So we don't usually think of these things in advance. If somebody said, here's all the equations of fluid flow, you wouldn't say, I predict hurricanes. People haven't been able to do that. But now, of course, in our computers, when you put it all in, you do predict hurricanes. So the universe is complex, chaotic, and history dependent. So that hurricane happened that way because of history of what came the previous week, not because of just hurricanes happen. So just a lot of wonderful things to think about. This is part of the story of why the universe appears to be so complex and why basically astronomy, biology, chemistry, physics are very much observational sciences. You have the basic laws, but you cannot calculate in advance things like that, at least not very well. So some examples of complexity. Well, Murphy's law is an example. There are more ways for things to go wrong than there are to keep things going straight. Second one there, that actually is a personal experience. If you do not test it, it will not work. My thesis project at Berkeley did not work. And the reason that it didn't work is we didn't test it enough. Whether we could have tested it enough, that's another subject. Anyway, a very deep personal lesson. If you do not test it, it will not work. It's almost a guarantee. So other things you can sort of summarize from here. Every organization will be attacked because there's entropy to be gained by attacking something big. So all these great monopolies in business, in political power, they are going to be attacked because there's energy there. as Willie Sutton supposedly said, but apparently didn't. I robbed banks because that's where the money is. So spontaneous heat engines occur because that's where energy flows, and you can extract entropy and do that. Another point, obviously, to make here, everybody's interested in climate change. It took the Earth something like 60 million years to put all the coal in the ground, and it's going to take us of order 1,000 years to burn it all up. Clearly, we are a geological force, even if some people don't like that idea. So lots of things to think about there. But here's a sort of more thing that was close to my question when I was a child. Okay, Dad, how can we get life? So this is another example of spontaneous complexity occurring because there's entropy to be released if you can create an organized structure. So we don't actually know how it works. Back to the beginning, as the cartoon says, I think you should be more explicit here in step 2, where it says a miracle occurs. When I was a kid, people believed that random assembly of atoms to produce a complicated thing like life must require a miracle. And we had people who said they knew how to do calculations of probability, and they were clearly wrong. So somebody says, I can prove something's impossible. Well, it might not be. Somebody's quoted as saying, if you can get a Nobel Prize winner to tell you that something's not possible, get another one. At any rate, we don't know how it happened, but at least we think these days it's not requiring a miracle, and now we'd just like to know how did that work. So now I want to come back to even more basic things about the expanding universe. So in 1929, Edwin Hubble drew us this graph. Here the little dots and circles represent galaxies. A galaxy is about 100 billion stars orbiting around a common center held together by gravity. On the horizontal axis is the distance that he thought they were away from us. On the vertical axis, how fast they're going away from us. And you see this rather dramatic trend. The farther away they are, the faster they're going. So if you divide the distance by the speed, you should get the age of the universe. So this in 1929 is the first time we ever knew there was an age to the universe, that you had any idea what it was. As it happened, he was wrong about the distance scale. So he got 2 billion years, and it should have been 14. So it didn't take too long before we had evidence against it. That was all very confusing for people. But basically, this is a true story, except for that one mistake. So also notice in the lower left corner, there are a few there with negative velocity. That means they're heading toward us. So in a few billion years, some of them are going to hit us. And that will be very dramatic. And I would like to be an astronomer at that time. On the other hand, I'm not going to make it. And in fact, by then, the sun will be too bright for life to exist on Earth at all, as far as we can tell. So we probably don't get personally to witness that, but maybe our descendants will move to another planet and survive that event. At any rate, 1929, the same year that the economy collapsed around the world, we discovered that the universe is expanding in this way, and it was a big shock. Einstein didn't think it would happen. He was wrong. One of those few times that he was wrong. So after that, let me see what happens next here. Push the button. So in 1974, I finished up at Berkeley in graduate school, having a thesis project that failed to do what this satellite did. So 6 months after I got out, I had a postdoctoral position at NASA in New York City. And NASA said, we want proposals for new satellites. I said, boss, my thesis project failed. We should try it in outer space. And he said, okay, we'll call up our friends. We'll write a proposal. And it was very thin. And it said, we've got an idea. And we're really brave young people. We didn't have any idea how hard it was. But eventually it did fly. 15 years later, it went up into space. And that's it, illustrating that it has instruments protected by a shield in the center. 2 of them are cooled down to 1.5 Kelvin by liquid helium. And it was to look at the Big Bang and look for galaxies after the Big Bang. So darn if it didn't work. So they did test it enough. So this is the number one thing we got. Within a few weeks, we're able to draw this curve which tests the Big Bang. The theoretical prediction is the smooth curve, and the measurements are right on the curve. We got a standing ovation from the astronomers when we showed this. And I was a little mystified at first. I thought, don't you know that's the right answer? But of course, we didn't have an answer book. So no, we didn't know that was the right answer. And so anyway, this is a measurement of the spectrum. It says how bright the light of the Big Bang is at each different frequency. So this is the heat, the radiation that still fills the universe left over from the earliest moments. And okay, so we got it about right. Expanding universe story is about right. And after some more years, the error bars went down to 50 parts per million, and you can't see them. So next thing we got, a couple of years later, we made a map. So this is microwave remote sounding extreme. So the map in the lower right corner is a map of the entire sky measured with the temperature of the cosmic microwave background radiation. And the hot and cold spots are 30 microkelvin difference from the average. The average temperature is about 2.7 Kelvin. So very small variations, but we got them. This was the first map anybody ever had that showed the Big Bang was not equally bright in every place, equally dense in every place. So Stephen Hawking saw that. He said, that's the most important scientific discovery of the century, if not of all time. And I didn't know why he said that right away. I was really pleased anyway. But why do we care that this is the picture? So number one, we wouldn't exist if there were not primordial spots like that. This tells us that the early universe had regions that were more dense than average. So there's enough gravity to stop the expansion of the material and pull it back. So we're here because there were some places that were dense enough to stop expanding. And we measured them. At least statistically, we measured them. Second thing is, most of them come from dark matter, which we can deduce but have never seen. It's presumably flying right through your body at all times, and you never feel a thing. The number three thing is, if we ever know what made the spots, we might understand quantum gravity, which would be a tremendous, satisfying moment for Albert Einstein, who looked for it but never could find it. So there are a lot of things in that chart, and this discovery then led to an industry. Thousands of astronomers worldwide have worked on making better measurements, including 2 more satellite projects that are up there, and we're not done yet. So there's more to learn, but anyway, this sets our measurement of what was the universe like when it was very young. And if you are good at this, you should be able to say, well, what would happen next? So just to summarize what we call the Big Bang story, I call it the expanding universe because when you call it a Big Bang, people think it's a firecracker, a localized small explosion. And we actually have exactly the opposite thing in mind. We have an infinite universe expanding into itself, the exact opposite of a firecracker. There's no center and no edge that we can find. There's not even a first moment. So when people say a firecracker, you imagine, well, of course, there was a time when it happened. But that's not true of the universe. If you try to imagine what is the smallest positive number, you cannot. There is no smallest positive number. And so similarly, as far as we can tell, there is no smallest amount of time in the universe. As you imagine yourself back and back and back towards the earliest moments, eventually you run out of imagination about the laws of nature, and you say, well, maybe that's the Big Bang, and we run out of imagination. So we should be able to say what happens next. But it's too complicated, so take a picture. So here's the great Hubble Telescope. It is 29 years old, almost 30 next month. Since it was launched, and it's still working because astronauts went up 5 times to upgrade it, fix it, and fix the big mistake that we made when we first built it. Anyway, we're thrilled that it's still up there and running, and it probably will continue a long time. So with it, we take pictures. Here is a very famous picture we took with it. It's called the Hubble Deep Field. So they decided to point the telescope in one direction where there were only a couple of stars for a couple of weeks and see what turned up. So astronomers thought we were going to waste our time. But what we found was thousands and thousands of galaxies in this one little piece of sky. And the answer to the big question of, could we see the first galaxies being born was, no, you can't. They should be in here, but they're not. So why are they not here? They're too faint and they're too red. So this is a beautiful picture. You see some of the galaxies have shapes. Some of them are just little tiny red specks. And those would be the ones that are the farthest away and the faintest and the earliest in the universe. And astronomers looked at this and say, this is beautiful, but please build us another better telescope. So they wrote us a little book. And so they said, build us what we now call the James Webb Space Telescope. So anyway, this is to be explained, and it's not fully explained yet. We also got a supercomputer program going. And if you believe what I said, we've measured the initial conditions of the early universe. We say galaxies should grow according to gravity. We just put all the laws of nature into the computer and say simulate with particle codes, just as you do with the air and the water here on Earth. It's a particle hydrodynamics, except we have to put in relativity and a few other things, and different chemistry. Anyway, here is a simulation of a rotating box of early universe, and you can see it pulling itself together to make galaxies and arranging them in huge structures. Once in a while, you can see through the picture that, like right now, you see its edge on. It looks like it's spontaneously made sheets of material. When it started out random, now become flat. And the sheets of material have strings through them. So, whoa, why is that? Well, it's just the way gravity works. It's beautiful. So, by the way, you see explosions happening. These are in the centers of galaxies. Explosions happen for two reasons. One is that when big stars get old, they blow up. And one is that black holes can form, and if material falls into a black hole, it can release a lot of energy from gravity. So, pretty active and pretty violent place in the early times. And in this history, here we are up at 8 billion years have passed. Still no solar system, by the way. We turn up when the universe is about 9.2 billion years old. So right about this in the movie, the solar system is being born in one of those little specks, which is a future galaxy way out there. So that's our history. The solar system is 1/3 the age of the universe, by chance, I guess. Also, you notice the explosions have more or less stopped. As the universe gets old, that sort of slows down. It's handy for us. We wouldn't like to be near one of those explosions, probably fatal for life. So the fact that we're on the outskirts of our Milky Way galaxy has protected us from those. Anyway, I think this is the most beautiful movie I've ever seen. And it tells you a lot of things that you could never tell by looking at a picture of the sky, no matter how many pictures you take, because this has time in it. And so now astronomers are taking those movies and saying, well, if that's true, then what would a picture of the sky look like? So we're getting to that. How can you test the movie? See if does it tell you the right thing? So we're coming up on that next one. So here's another Hubble picture. There's something called the Whirlpool Nebula, obviously. And it has this partner galaxy next to it, and they're about to merge together in the next few 100 million years. A great collision will occur. And the sketch in the lower right corner was from 1845. There was an Irish astronomer who was a royalty, Lord Rosse. He built a telescope that was about 6 feet across with a big piece of metal for a mirror. And he had to climb up on a huge ladder to be able to use this thing. He was good enough to draw pretty much, he got it about right, didn't he? I think that's a thrilling consequence of early astronomers. He got the little galaxy and the big galaxy and the spirals. So anyway, it was possible to make progress in 1845, even before photography. Anyway, this is another beautiful picture from Hubble. This shows the Crab Nebula, which is a star that blew up, and we know exactly the day that it did it. This was in AD 1054 on July the 4th in our calendar. And we know because it was seen everywhere in the world, and some of the records still exist, especially from China. So anyway, this is the debris flying apart from a star that blew up. It's important for us because those are the kinds of explosions that to produce the chemical elements we see around us. You see carbon, oxygen, nitrogen, phosphorus, iron, calcium especially. Where did they come from? Where did the Earth come from? It was debris from things like this that blend back out into space. The nuclear reaction products from the star had burned up hydrogen and helium and made them into those things. Gets recycled. So all of the atoms in your body were made in that way. There was no hydrogen, only hydrogen and helium and traces of other things in the Big Bang. So all of our atoms have been somewhere. A rather dramatic trip, and you don't feel it. The atoms have no memory. But at any rate, you can say, I'm star stuff. That's how it works. So now we'd like to say, well, how do the planetary systems grow? And here's one thing that we've done. Worldwide effort to build this radio telescope in Chile. It's called the Atacama Large Millimeter Array. And the picture in the upper left is a picture of a solar system being born. What we see is the heat radiation coming from dust grains that are orbiting around a future star. And you can see them, and you can see that they're in rings. And the hypothesis is there's a planet growing in each of those dark spaces in between the rings. And that if you would come back in 100,000 years, you would see the dust would be gone and the planets would still be there. So our descendants have something to do. See if that actually happens. And we've got dozens of pictures like this now. So this kind of thing was predicted. One of the few things we probably predicted about right. And so now we've got a story to tell you. How does the solar system grow? Something like that. And here's a story that may or may not be true, but I show it anyway. This is a movie of the early solar system. And what we see are the 4 giant planets in their orbits, the Jupiter, Saturn, Uranus, and Neptune, surrounded by little green rocks, the asteroids and comets that are leftover debris from the formation of the solar system. Well, when Isaac Newton told us about gravity, it looked to everyone like, well, the solar system runs like clockwork. Well, it does pretty much, except it isn't guaranteed to do so. So it's possible for it to become unstable. So that's the point of this movie. It is possible for ordinary gravitational energy exchange between the planets to change everything. So this may be wrong, but it makes an important point that what looks to be forever isn't always. So a thing that it tells you also is there's a reason why we got bombarded here by asteroids and comets at a certain point. When this movie was made, people were pretty sure that it happened about 800 million years after the solar system started. Now we think maybe that's wrong, but something like this apparently maybe did happen. So when you want to know why is the Earth like it is, that's part of the story. The little rocks flying over everywhere, they would be the things that brought the volatile materials, the carbon, the hydrogen, the water, things like that that would have burnt off the young Earth when it was just a hot rock. We got them later by some process sort of like that. So if you want to know about the internal structure of the Earth, you need to know part of this story. Okay, so now I want to talk about the Webb telescope that we're working on now. By the way, who is James Webb? Why would you name a telescope for him? He was the second administrator of NASA. He was the guy that went up to Jack Kennedy with a plan for the Apollo project. And Kennedy was convinced enough to say, let's do this. So 8 years after they had this conversation, we actually had people walking on the moon. We can't even have an argument that fast anymore. So you have to say that was a kind of miracle, a personal miracle. Of course, we were driven by desperate fear of the Soviet Union. When I was a little kid, they told us, in case of a nuclear attack, hide under the desk. So even when you're 8 years old, you know that's not enough. But at any rate, it propelled the United States to invest heavily into science and technology and engineering. And we still see the fruits everywhere. We can do what we do today, at least in part, because of that terror that we felt 60 years ago. So anyway, now we can build a telescope like this. So why can I ask Northrop Grumman to build a telescope like that? Because they build other telescopes for other government agencies. So we're still living off that conflict that we have, but let's also do something good with it besides surviving to the next year. So we are organizing this at NASA. Our Goddard Space Flight Center just down the road is where the management is centered, and our project manager is there. We chose a big company called Northrop Grumman Aerospace. And just to give some perspective, by the way, the corporate budget is about 100 times the budget of the telescope. So it tells you that even though this is a big deal for astronomers, this is a small deal for the world. Anyway, it has 4 instruments that I'll show you briefly later. It will unfold after launch because it is much bigger than the rocket. I will show you the movie of how it unfolds. The big hexagon, the golden hexagon mirror, is 6.5 meters across, so it's about 21 feet. It's about 2.5 times as large diameter as the Hubble Telescope. So it's a huge, huge technical engineering accomplishment. And of course, we're doing it for a reason. We think we're going to see something important. It is allowed to cool itself off to very low temperature. The mirror there will be about 45 Kelvin, 45 degrees above absolute zero. And why would you do that? So that it doesn't glow at infrared wavelengths. We need to get the telescope so cold that it doesn't emit its own infrared light, because that's what we want to see is infrared. So this is a sketch of the steps that it has to take. We built the telescope up with the instrument package at Goddard Space Flight Center. There it is in the upper left corner. Then we put it in a big plastic tent and put it on a shaker to see if it could survive launch. It made a buzzing noise we didn't like, so we had to stop before we broke it. We had to deal with that. Then we finished that. We put it in a big shipping container, sent it around the highway to Andrews Air Force Base, and the entire truck went into the airplane with about an inch clearance all around. It flew to Texas, and we got it out again and tested it in the biggest vacuum tank we have. It's the one we used to get the astronauts ready to go to the moon. So we tested it there. It worked. We put it back on the airplane, sent it to California, which is where it is now. And we have joined it together with the rest of the observatory, the warm part. And it is now in the final configuration that it will be. We're about to go do one more last vibration test on it. And then we will button it up, put it in a different shipping container, and put it on a boat. The boat will go through the Panama Canal on its way to the launch site in South America. Why do you choose South America? Because that's where the Europeans have a company that launches rockets. It's French Guiana. It's actually a piece of France, and it's almost on the equator, which is good for rocketry. Anyway, according to plan, we should be shipping there at the end of this year, and then early next year, launch. So we have a lot to do between now and then, but that's the plan. So then it will be up there, and what happened to my picture anyway? Now I want to show you a movie of the unfolding telescope. This is the thing that makes it possible to get a telescope 6.5 meters across into a rocket that's 5 meters in diameter. So this is an extremely complicated origami problem, and it's been solved. Mostly, we hope. I'm crossing my fingers, even though I'm not superstitious, because there are many, many things that have to go right for this to work. So it's very complicated. You'd say, why is it so complicated? Number one, because it has to be cold. Number two, because it has to be big. And if there were any other way that we knew of to get at the science, we would do it that way, because this is so hard. But at any rate, we can do it. And this movie that you're seeing here in about a minute or two is representing about 2 weeks' worth of work after launch. So this is all done by remote control. We send commands up to make each of these steps happen. If you're worried about whether it can happen, well, of course, we have 2 of everything where you possibly can. There's motors all over. Every motor has 2 sets of electrical windings and 2 sets of controllers. So a random failure of some electronic part is not going to stop it. It is possible to have enough failures to stop it, but at least one part at a time, we've ruled that out. So there it is. It's unfolded, and it'll still take a total of 6 months to get it all set up and focused before we start showing you science pictures. It's a long process, and it will be very intense for us at the control center. So there it is. That's the telescope itself. So what are we going to be able to look at? Well, faint things and bright things. If you're a bumblebee hovering out there at the distance of the moon, we'll be able to see you, both reflected sunlight and the heat radiation that you would send out. Time exposure needed, but so please don't move. But this is an astonishing thing. When we calculated this, I thought that can't be right. But it is right. You could see a bumblebee if it would sit still. The harder problem is actually to look at bright things like Mars, which we care a lot about, but it's so bright we almost can't do it. But we've got our ways. So we'll be able to see everything from Mars on out to the rest of the solar system, on out to Pluto and beyond. So here are a few pretty pictures to illustrate what we hope to get. This is the Eagle Nebula, where stars are being born today, inside this dusty cloud. And you can't see inside. You can't see the stars inside because the dust is opaque for visible light. But if you had longer wavelength, you could see through the dust cloud. So why is that good? Well, because light has a wavelength, and the longer the waves, the more they can bend around something. When you go off to the security at the airport, they look through your clothes with something, they use longer wavelength light, millimeter waves, and they can see right through the fibers of your clothes. So they can tell you if you're wearing something you shouldn't be wearing. In this case, we are able to look past the dust grains to see inside the clouds. And now you see lots and lots of stars. And so this is an example of things we're going to be looking at. Star nurseries, places where stars like the sun could be being born today. We'll be looking at places in the solar system. This is Europa. It's a satellite of Jupiter that was discovered by Galileo himself. This picture came from a mission we called Galileo. And it shows that Europa is a little, it's not quite as, it's a little bigger than the moon is, I think, our own moon. And it's covered with ice. And under that is an ocean, probably salt water. And it's a good guess that maybe if there's life in the solar system besides here, an ocean would be a good place to look. So Congress has been enthusiastic, and we've been working on what you're going to do when you get there. So there's a mission called Europa Clipper, which would fly out to this area. After that, people want to do a Europa lander. So where would you want to land? Well, it would be really good if you could land on one of those cracks where water comes spritzing out. So there are actually little geysers that come out from time to time. And if you went there, you could analyze, if you just fly through the plume of material, you'll be able to do a chemical analysis of the water that's coming up out of Europa. You might see organic molecules. That would be interesting. So when we first discovered this, people thought, well, obviously you've got to melt your way in with a nuclear reactor. But no, you don't. You can just go where the stuff is coming out. So we'll be looking at these also. If you watch enough stars long enough, once in a while you see a planet go in front of a star. The star will begin to blink like this in the movie. And you say, well, that's interesting. Now I know there's a planet there. If you're very good at this, you can say, well, some of the star... Can you hear me in the back without the mic? Okay.
For the online people.
Oh, here's another mic. Yeah, is it better? Yeah. Okay. So this shows that planets go in front of their stars. We've got thousands and thousands of them in the catalog. We know where to look and when to look. So we can do that chemical analysis. So with the Webb telescope, we're hoping to see signs of water on planets around other stars. Small planets. I don't think we're likely to see signs of oxygen. Of course, we would be thrilled if we do, but we don't think we're going to do it. Okay, next. So are there other planets like this one? Well, maybe, but not very often, I think. So there's Earth in the solar system is a very special spot. We have the right temperature to have liquid water. We have a very nearly circular orbit, as most of the planets do. We're the only one with a moon as big as ours that's so close to us. So that's pretty important for our climate, for our weather, for the tides, and it stabilizes the spin axis of the Earth. So it's more or less the way that it is now, has been for probably for many, many billions of years. It has a big magnetic field, which protects us from cosmic rays, and has just enough water to give us both oceans and continents. I don't know if other planets did have that situation. It would be interesting to go find out from Venus whether Venus did have continents and oceans at one time. And we certainly have evidence that Mars had some water and lakes, at least. But it's gone now. So interesting questions about why is Earth special. Also, the sun is a good star. It's not too dangerous. It behaves itself. Little red stars, which are very common, are always having eruptions. And you could imagine life could tolerate that if it was under the water, but it wouldn't be living on the surface like we do. So if you're looking for intelligent life, probably can't find it around other stars that are more dangerous. Anyway, and something that's quite special for us, we're the only planet that we know of that has plate tectonics. So we think that that's a possible reason why we have life, because the atmosphere has been exchanged with the subsurface, and there are places where warm water comes bubbling up, all enriched with minerals, and some people think that's where life originated. Have you seen the pictures of the chimneys that come up out of the ocean? If you were trying to build a reactor that would try every possible combination of water and minerals, let's build a chimney with thousands and millions of little tubes. So I think that's nature's experiment, and it might have been where we all came from. So, of course, astronomers don't only build telescopes for space, we build them on the ground. These are 3 giant telescopes that we are working on now. The biggest one is European, it's 39 meters across. It's 6 times as big as the Webb telescope, and they're already building it. So it's going to be very, very powerful. This should be up in about 5 years, 6 years, should be up and working. I'm thrilled. So I just wanted to show you very briefly that we have a technology to enable those giant telescopes to get a sharp picture. So the atmosphere is all turbulent, and so we have to do something about it. And we have something called adaptive optics. And so we say, well, if I know that thing out there is a star, let me adjust the telescope to make a sharp picture of the star, and the neighborhood around it will also be in focus. So that's pretty good. We've known about the idea since 1953. Now, as it turns out, we can do it for your eye doctor, too. Your eye doctor needs to see through the natural lens of your eye to see what's going on. And if you're a football player, you want to say, I want the very best eyesight possible. You can get LASIK, and he's twice as bad. You can see twice as well as I do. And then, anyway, so now your eye doctor has it. In fact, the person that figured out how to polish the Webb telescope mirrors invented this system on the right. So you never know how things are going to connect. So this is my current idea, but I'm thinking about out of time. So I'll just say very briefly, if another way to look for planets around other stars is to block the starlight with a thing that casts a shadow. So this is my crazy idea. Put up something 100 meters across orbiting the Earth, cast a shadow of the star onto the telescope on the ground. This is another flavor of many things, but if you could do it, you could get a picture like the one on the right in about a minute. And we would be thrilled, but it's probably not going to happen right away. It's too hard. So people want to know, well, can we go to the other planets? And I think the answer is pretty surely no, no time soon. The farthest we can get as humans in the solar system is the moon and Mars, as far as we can tell. Other places are pretty hostile, and you wouldn't like it when you got there. You can clearly build a robot to go anywhere, and we already have. But even in the future, when the robot is computerized and has an intelligence of its own, it'll have to be extremely patient to get to another star. So all those stories you see on TV, not happening. I'm sorry. But anyway, even robots will need to be patient. So let's wrap up, and we have a few minutes for questions. Thanks.
Questions?
When you do the unfolding procedure for James Webb, is that going to be, when you're doing the unfolding procedure of James Webb's, is that going to be near Earth in orbit or after it gets to its Lagrangian
So his
spot?
question is, when are we unfolding it? And we're actually most of the way out to the place we're going, which is called the Lagrange point. It's about 1.5 million kilometers out. So we're most of the way there by the time the thing is unfolded. We pass. Yeah, it takes 5 seconds for the light to get there from here, for the command to get there from here. So the solar system is big, but we're staying as close to home as we can and still do this project. Okay.
Which Lagrange point?
Which Lagrange point it is going to be the second Lagrange point. It's between the Sun and the Earth system. So Sun, Earth, and the Lagrange point all in a row. So it's a point that's 1.5 million kilometers farther from the sun than we are. And the telescope orbits around that area. It's a good place because when you go there, the sun, Earth, and moon are all in the same direction. You can put up your one-sided umbrella and keep the telescope cold. It's named for Lagrange, but it was actually discovered by that guy, Euler, in 1750 with his pencil.
Yeah, you showed two models of the solar system with different amounts of rock around them. One of them they dissipated, the other they didn't. What was the difference between the two?
That was actually just one model where the rocks got kicked out by
you
the
just had to
gravitation.
wait for a long time before they suddenly decided to depart.
Yeah. So a more recent story says, well, the observations are against this. They say, well, it happened a lot quicker than that. We'll find out.
Hi, with the discovery of the pockets in the universe, in the early universe of different temperatures, do you have any hypothesis about what caused those to occur? What was the reason for that differentiation?
Well, I think if we could answer your question, whoever could answer it right would be getting a Nobel Prize. The general speculation is quantum mechanics did it. But maybe thermodynamics did it. But we don't know. So come back in another 10, 20, 50 years, somebody may have an answer to your question. There's work for the scientists to do yet. You're not to the end of science.
I just have a question about water detection. How far will you be able to detect the water, and with
how far can we detect water in
and
other
then
planets?
with what confidence level?
I think for us, for this telescope, it's not very far. We don't have very many planets that are just right for us. But future telescopes are intended to do that. So this thing that we've done here is just something that we think we could do. It was not an objective. So if you were going to design a telescope especially to see those molecules in other planets, you would design it differently. Probably bigger and harder. But of course, we're ambitious, and astronomers are working on that.
When you use a ground-based telescope to look at a target in space, do you apply atmospheric correction algorithm to get the actual radiance coming from the star?
So his question is basically, how do you deal with the fact that the Earth's atmosphere blocks the view of your distant targets? And yes, we have to calculate how much has been lost as the light comes to the telescope. So we have a lot of different ways, and we are probably not correct.
Like we also use atmospheric correction because we do the other way, like from space we look at the ground. So I think that's one common thing
It's a
where
similar
we can
problem.
Move forward.
Yes, Earth scientists have the same problem, only you have to do it better than astronomers have to do it. I'm just beginning to learn about it, but if you're an Earth scientist, you need to know, has the Earth changed by 0.1% in a decade or a century? And astronomers hardly ever need to be that good.
Yeah, but anyway, we need to learn from each other, I guess.
Yeah.
If an event happens, how quickly can you reorient the telescope to look at the event?
Okay. How quickly can we reorient the telescope? So in principle, we can turn it to another part of the sky in about an hour. But if you give us a phone call, we promise take 2 days. We'll do it within 2 days. Because most of that time is people deciding what to do and reorganizing the commands to the telescope. But we expect to get that phone call quite often.
In the examples that you gave of how nature behaved, it would seem to me that nature tends to increase entropy on its own. However, on the computer simulation that you were showing, it would seem to me that entropy was decreasing a long time. Or did I get that wrong? Or
yeah, you get it wrong because we all do. We see a lovely, beautiful structure or growing in front of us, and we think, oh, that's ordered. So where is nature hidden the entropy that increased while it did this? So the entropy went into the heat around things. So as an example of something you wouldn't expect, but is kind of obvious when you think about it, if you have a little Earth satellite orbiting the Earth and it feels atmospheric friction, it loses energy and it spirals in towards the center of the Earth, but it goes faster as it's falling in. So it's kind of heating up. So it's converting gravitational energy, which is potential energy, into kinetic energy. So nature is spontaneously heating itself up from gravity. And when it does it enough, then it can turn on the nuclear reactions, which heats it up some more. So the sun is running because of that. So as I'm trying to explain, nature spontaneously produces more entropy while it makes something that looks to us ordered. The entropy is hidden where you don't see it.
Well, that's one way of answering the question, but Fang Liji and later Dyson pointed out that self-gravitating systems basically do not satisfy the chemist's concept of thermodynamics, and they can have decreasing entropy automatically.
It's tricky. You're quite right. Astronomers call it negative specific heat. Right. So, well, you don't see that in the lab, but we see it in the sky. Negative specific heat means spontaneously heats itself up, converting gravitational energy into kinetic.
A follow-up question. So according to the second law of thermodynamics, the total entropy increases in an isolated system. So do you think the universe is an isolated system?
Well, I don't know I don't actually know how to answer your question. It's presumably infinite, probably infinite, but we can't prove it. So you can say, well, let me take a box of universe and see within a piece of universe, is that isolated enough? And so I think the answer is yes, the entropy will increase in your isolated box of universe. But why does it? It's some of the entropy is being hidden. So as we create these concentrated gravitational structures, it looks more and more ordered, but the heat went somewhere. So the entropy really did increase. It's really tricky when you start converting mass into energy.
What is the projected lifetime for the James Webb?
Oh, how long is the Webb Telescope supposed to last? We're carrying fuel for 10 years of operations. And of course, you can't prove something's going to last, but that's the plan. And if we're lucky, it'll last a lot longer. And if we're unlucky, it won't. Yeah.
We have 2 online questions. The first one, if Hubble was serviceable 5 times, don't you think it's a problem that the Webb isn't going to be serviceable at all?
Yes, it's a challenge that the Webb Telescope cannot be serviced. It is too far from Earth. We don't have any equipment that's ready to go there. It's not logically impossible. So we will be painting a big pattern on the end of the observatory. So if you send a robot, the robot can grab on and do something. But our plan is build it so it doesn't need to be serviced. So that's why it's so hard right now.
Thanks. Second question.
Test and test and test. Yes.
Second question is, what are the project management lessons for future large science projects from the massive underestimation of costs and time to develop and launch Webb?
Good question. Well, number one is when somebody says it's easy and cheap, don't believe them. I'm recalling when we started the Webb Telescope, we were under the management of Dan Golden, who was a very fascinating person, but he insisted on faster, better, and cheaper. We should have all 3. And my fellow scientists and engineers said, well, which of those are you going to give up? Because you can't have faster, better, and cheaper. So anyway, the thumb was clearly on the scale. We should all come up with small estimates for the price of stuff. His instruction was find a way to do this telescope for $500 million. People laughed at us from the very day that we said that. So we sort of knew that couldn't happen. But anyway, you can't really know the right answer until we get farther into the project. Until you've actually got a design and have a plan that includes everything, you can't really know the price, even what it should be. That's not even accounting for the mistakes that may happen. So anyway, we have a hard time estimating really big projects. For small ones, which should be easier, you would say, well, why don't I just add up all the pieces that I know I have to build and then multiply by some uncertainty? So that's the way we like to do it, but it doesn't also work that well either. So we have an even simpler method that says, well, how much does it weigh? and multiply by some number of dollars per kilo. And that turns out to be almost as accurate as adding up all the pieces. And the advantage of that one is you don't have to be smart, and you don't have to prove that you know what you're doing. And it builds in some caution. You say, you can't get away with saying, I'm so much smarter than my predecessors. So if somebody had done that on this telescope, it would have come out more or less what it is. But we didn't like that answer. Dan Golden didn't like that answer. Anyway, so it took us a long time to get to where we had a good answer. And even then, it's hard. Yeah, so that's a very difficult question to answer well. I'm just giving you some of my opinions.
Thank you.
Any other questions? Okay, let's thank the speaker again. And we do have the book signing after we set up the table. Yeah.
Okay, thank you.